Hello everyone, my name is Arip S. I'm going to explain you about the simulation of different open channel shape and Manning's value using HEC-RAS software. This is part of the project from fluid mechanics class. So what is open channel? Open channel is the flow of liquid with free surface. So therefore the interface between water and air. In other words, water flow through a passage under atmospheric pressure is called flow in open channels. Here are two example pictures from Civil Today and USGS. So the question for my project is how can different shape of open channel can affect the flow of fluid, and how can different type of channel, which can be explained by Manning's coefficient, affect the flow of fluid. So I have these two questions, and it will be phase one and phase two. And you can see from the table that the example of the shape of open channel and how can we calculate the speed based on the Manning equation with different Manning coefficients depends on the bottom of the open channel. What will we learn? What will the viewers learn from the projects? So I hope the viewers can learn how different shape of open channels can influence the flow depth, velocity, or efficiency under the same flow condition. Also, I hope the viewers can see how changing the Manning's roughness coefficient, which represent the materials like concrete or natural riverbeds impact water movement. And by the end of the video, I hope the viewers can understand how engineering design choices such as channel shape and surface type play a critical role in hydraulic performance, flow control, and efficient water conveyance. So here I'm using the HEC-RAS for one dimension or steady flow. First, we need to create the geometry of the riverage. So I created the geometry of the riverage uh, from station number 9 to station number 1 with 800 meters long. And then I created the cross section of the open channel. I made three different cross section: trapezoidal, triangular, and rectangular shapes. And then we need to define the flow rate. So I put the flow rate or discharge about 65 cubic meter per second, and slope of the river 1 by 800 or 0.005. And for the Mannings, the roughness of the riverbed will be 0.012 that represent finished concrete. Here is the result from the trapezoidal. The blue color is the water filled or flow through the open channel. Uh, and then this is the station number 9. Has elevation 8 but the bottom elevation is 8 meters, and station number 1, which was the downstream, is 4-meter elevation. And here this is the cross-section result, and here we can see the profile plot from the upstream to downstream, and then also we can see the cross-section output, like how is the velocity, the elevation, the flow rate, And then this, and here on the right side is the XYZ or 3D perspective plot without the flow of water and with of the flow of water. Here we can also can get the result of each station from upstream station number 9 to downstream station number 1. The float, we can see the result of the discharge, elevation change, flow area, and the flow number. And we got the flow number 0.63, which show that the flow is subcritical flow. This is the result from triangular cross-section. And then also the result from each station from upstream to downstream. And then this is the result from the rectangular shape of the open channel. So that's the first phase. How about the second phase? Second phase is we are using the same geometry. I chose the trapezoidal shape because it's common shape of the open channel. And I changed the Manning's equation or different type of riverbed: unfinished concrete, clean excavated earth, and major river. There is the result. This one is the result from the unfinished concrete. I'm sorry, this one is from the major river. And this one is with the clean excavated earth, and this one, the combination of the uh, three different riverbed. And you can see that the uh, major river has the highest, I'm sorry, the major river is the highest elevation. So this is the result of the first phase. Using the same discharge, same slope, same Manning's coefficient, but different shape of the open channel. If we see the flow area, we can see that the rectangular shape has the largest area. Therefore, this shape has the highest capacity to collect water at a given velocity. And for velocity, the trapezoidal is the fastest with 1.8 meter per second, while a rectangular has the slowest velocity with 1.4 meter per second. And therefore, this shape, the rectangular, is the least likely to cause erosion. How about the Freud number? We can see that if we know that if we have Freud number less than 1, the flow will be subcritical, and all the three shapes showing all the three shapes has Freud number less than 1. So all the shapes having subcritical flow and within the typical desirable band. So the hydraulic stability is okay for all. And for the depth, the flow depth, triangular, the orange is the deepest with 1.58 meters, which may reduce the freeboard or increase the excavation cost. And rectangular is the shallowest with 0.7 meters, which can be easier to inspect or maintain, but maybe freeboard if you need to handle floods. And for the second phase, phase number 2, which we have the same open channel shape, but different uh, riverbed materials, like different roughness based on the Manning's value. For unfinished concrete, here we have the depth about 0.88, velocity 2.58 meter per second, and flow area is 25.18. Also, it has float number more than one, therefore the flow is supercritical flow, which means fast flow. Shallow flow but fast. That is flow that is erosive and can cause hydraulic jumps when it meets the downstream slower ridge. So this kind of this kind of result is normally avoided unless it's specifically designed for spillway. So we need to modify the design to avoid supercritical flow. And for clean excavated earth, it has depth 0.9 meters, velocity 20.5 meter per second. It has area 26.05 square meter and fruit number almost uh, almost reach 1. So it's nearly critical flow. So it has unstable and risky. And with this speed, 2.5 meter per second is likely too high for unlined earth channel, which means high risk of erosion. As for major river bed roughness, it has the depth of 1.15 meters. Velocity is the slowest one with 1.80 meter per second. It has flow area of 42.97 square meter and float number 0.63 or in subcritical flow. So subcritical flow with moderate velocity and largest flow area. This we can say that this is generally the most stable and desirable for routine conveyance. So the conclusion is for the first phase, trapezoidal is the best overall choice, maximum capacity with maximum capacity and minimal erosion concern due to the slowest velocity, flow velocity. And for the second phase, the major river case is the best design of the three with subcritical flow, moderate velocity, and largest capacity. Therefore, the most stable and least likely to produce erosion or hydraulic instability. So that's all about the project. Thank you for watching. Bye.